Welcome to the continuation of our lectures in abstract algebra. In this lesson, we're going to talk about groups whose elements are called permutations. In the first few lectures, we actually have introduced permutations already. So to recall, if you take any non-empty set X, you can form the set of all bijections from X to X and denote the set by the symbol S sub X. Again, the set S sub X consists of all bijections from X to X. When you say bijections, these are functions which are both one-to-one and onto. And under composition of functions, we have learned that this set of bijections form a group. To further explain why the set will form a group, these are the details, no? If you have two permutations on if you have two bijections on X from X to X, pi and sigma, then their composition is also a bijection, meaning the set S sub X is closed under composition of functions. Secondly, you see that function composition is naturally associative. Thirdly, the identity function idx play as the identity element, because if you compose any bijection pi with the identity function, you see that the product is pi again. Finally, we have learned that if pi is a bijection, then it is an invertible function. In fact, we were able to show that the inverse of a bijection is another bijection. Furthermore, if you take their composition, you will see that because pi inverse simply reverses pi, the composition is the identity. These bijections, which are elements of S of X, will be called permutations on the set X. Normally, in this lesson, or in the future lessons, we will be more focused in the case when X is finite, although we will also consider the case when X is infinite. By the way, this group S of X under function composition is called the symmetric group on X. As an example, let's take X to be the set Z of integers. Now, I want you to fix on any integer k, and for this value of k, I want you to define the function pi sub k from z to z, so that it assigns every integer n to n plus k. So we are adding k to every integer. So you can imagine that in the real number line, every integer moves either k units to the right if k is positive, k units to the left if k is absolute value of k units to the left if k is negative. We can check that pi k is 1 to 1. For example, if you have two integers n1 and n2, and assume or suppose that if we suppose that pi k of n1 equals pi k of n2, then what do we need to prove? We need to prove that n1 is n2. But by definition, pi k of n1 is n1 plus k. And by definition, pi k of n2 is n2 plus k. Because these are integers, after all, we could cancel k and conclude that n1 is n2. Therefore, pi k is 1 to 1. Secondly, we can also prove that pi k is onto, because if you get any integer m, we could always consider the integer n, namely m minus k. So n is taken from m by subtracting k. So this is also an integer. Then we see that if you take the image of n under pi sub k, get n plus k as the definition tells us, but n is m minus k, so you get m as a result. Meaning to say, every integer is also an image of pi sub k, and therefore the function is surjective. Combining these two results tells us that pi k is actually a bijection from z to z. And by a bijection from z to z, we mean that it is a permutation of z. Now, in statistics, you might have heard the definition of a permutation differently. In statistics, we consider permutations as arrangements of things. That is not really different. No? We only define permutations differently because it will be an advantage for us to treat permutations this way, as you will see later. You can see that the set of integers in the real number line gets also rearranged by shifting the number line k units to the right or to the left. You can imagine the integers as the blue dots, right? And for example, when k is 2, so pi sub 2 acts on the number line, or as if it's adding 2 units to every point, or it's moving the points 2 units to the right. So you see, after applying pi sub 2, everybody gets a new position, but so it seems like a rearrangement. I want you to first observe that the set pi sub k, the set of all mappings of the form pi sub k, where k is an integer, is actually a subgroup of S sub z, because you see, if you first of all, the identity function. So what's the identity function? The identity function on z can be considered as the mapping pi sub 0, because if you add 0 to anything, you get it stays in its place, right? So in other words, the identity function on z belongs to the, let's call this one h if you want, belongs to h. Second of all, if you get pi let's say n1 and pi n2 in h, if you take the composition of pi n1 with pi n2, what is the result? You see that moving the number line n1 units and translating the number line n1 units and then, or n2 units, and then followed by another translation n2 units, results to another translation by an amount of n1 plus n2 units, right? So therefore the product or the composition also belongs to h. Last but not the least, if you have the mapping pi sub n, what is the inverse? If pi sub n takes everything, moves everything n units, right? What's the reverse? It should, to undo the process, you have to subtract n units, right? So therefore the inverse is also in h. Therefore the collection of all these mappings actually formed a subgroup of S sub z. Another example is this. If we take the set x to be the closed interval from 0 to 1, and then consider the function g mapping 0, 1 to 0, 1, and this g is defined as follows: sine of pi x over 2. Now we can prove, or we can see, that this is a permutation on the interval from 0 to 1 by simply observing the graph. Now I've graphed for you the I've shown you here the graph of g on the interval from 0 to 1. As you can see, the range or the image is also the interval from 0 to 1. Why is this a permutation? Because it's clearly 1 to 1. It passes the horizontal line test. Okay. Second, it's onto because the range is the entire set 0 to 1 also, or the entire interval from 0 to 1. We can see that this is a permutation by observing the points, how it moves in the interval from 0 to 1. For example, if I take this 6 equally spaced points, right, in the interval from 0 to 1. After applying G to the interval from 0 to 1, their images will be these points. So as you can see, points near 1 gets squished together closer, right? So that's how the permutation, that's what's the action of G on the interval from 0 to 1. It's like squishing all the points near to 1 at a closer distance than those points which are far from 1. An interesting case is when X is a finite set. When X is a finite set, we simply choose the elements 1, 2, up to n as its element, because n simply counts the number of elements. As you can see here that 1, 2, 3, 4, and so on up to n only is used not to denote numbers. They are just used to denote elements of an arbitrary finite set. Instead of writing S sub x in this case, we simply use the symbol S sub n. And if pi is a permutation in S sub n, we will use this notation, or this is the notation used in abstract algebra for a purpose. We draw an array, a 2 by n array, where the first row are the integers or the symbols 1, 2, up to n. Corresponding to each element 1, we draw down, or we write down the image of 1 under pi. We write down the image of 2 under pi below 2. We write down the image of n under pi below n. Now, because the set X is finite, there can only be finitely many permutations that we can form on the set X. In fact, there are n factorial of them. Now you can imagine a permutation on the set 1 to n as a manner of, let's say 1 to n are applicants, right? Let's say you have n applicants to n different jobs. Then because the mapping is 1 to 1 and onto, then we can only assign only one job to each applicant, and after the assignment, no job should be left vacant. So the permutations on this set shall be the collection of all manners of the collection of all assignments of these n applicants to n possible jobs. In how many ways can we do that? Well, for the first position, because assuming that nobody is assigned at this point, then there are n choices for job number 1. Now, if one applicant is already assigned for job number 1, then we can only assign n minus 1 applicants for the second job, and so on, until you are left with 1. So by the fundamental counting principle, if we multiply n times n minus 1 times n minus 2 and so on times 1, you get n factorial. You may have seen the set S sub 3 from a previous lecture. In this case, because n is 3, we are really considering the permutations on the set 1, 2, and 3, right? So normally we draw arrows or diagrams to represent mappings or bijections. For example, before, we write the identity function this way, or we represent the identity function this way, right? But as you can see, drawing arrows can be a little bit inconvenient. So we use these notations now. For example, the identity function will just be denoted by this symbol. As you can tell, 1 is mapped to 1, so we write 1 under 1. 2 is mapped to 2, 3 is mapped to 3. For the element row 1 maps 1 to 2, 2 is mapped to 3, and 3 is mapped to 1, and so on. So we have learned that because 3 factorial is 6, there are only 6 elements for S sub 3. And these are the 6 possible elements. You can consider, for example, the number of ways you can arrange 3 children for a picture in a row. So for example, if their initial position is child 1, child 2, child 3, then row 1 denotes the permutation where you arrange now them in a row as child in the order of child 2, child 3, child 1, and so on. So there are 6 different ways to permute or arrange, or there are 6 permutations on a set of 3 elements. But remember, we are in group theory. These elements are elements of a group, so they can be multiplied. For example, if we want to know what rho sub 1 times mu sub 1 is, what do we do? Because mu1 and rho 1 are functions, and then the domain is the set X containing 1, 2, 3, so you might want to get the image of 1, 2, and 3 under the composition. For example, what's the image of 1 under the composition? Performing composition of function, the image of 1 under mu1, so you look at mu1, 1 goes to 1, so this is replaced now by 1. Now the image of 1 under rho 1 is 2, therefore the final image is 2. So the image of 1 under the product is 2. How about the image of 2 under the product? So we do similarly. Mu1 of 2 is 3. Rho 1 of 3, you look at rho 1, this is rho 1. Rho 1 of 3 is 1. Therefore, the image of 2 under 1 under the product is 1. Because these are bijections, then you can already tell that the answer for the last element is 3, because it should not repeat, right? Because of the one-to-one property. But if you want to compute, then you can also verify that the final image is 3. Therefore, as you can see, the product rho 1 mu1 sends 1 to 2. So we write it this way. Sorry. This one is rho 1. This one is mu1. So what's the product? Because the product sends 1 to 2, we write down 2 under 1. The image of 2 under the product is 1, so we write down 1 below 2. And the image of 3 under 3 is itself, so we write 3 under 3. Which, when you look at the 6 elements, this is actually the element mu sub 3. Right? We could actually multiply without doing or writing this by just looking at these factors. This is where the notation can be convenient. So remember, when you take composition of functions, we first apply whatever is on the right. So, for example, if you want to know the image of 1 under the product, you first apply mu1 to 1. So this is mu1. So you go here, 1 goes to 1 under mu1, and then this image 1 will be mapped by rho 1 to 2. So the final image is 2. So 1 to 2. For the image of 2, you start here, 2 goes to 3, and then 3 goes to 1. That's why there's a 1 here. For the element 3, you have no choice but to put there 3. But if you want to check, then 3 goes to 2, and then these 2 will be mapped by rho 1 to 3. That's why this is the product. Now, I've already done we have done the calculations before, and I produced this Cayley table for S sub 3. Now, what are the things that we can notice in this table? First of all, the table is not symmetric about the main diagonal, meaning to say the group is not abelian. For example, rho 1 mu1, right? Rho 1 mu1 is, what's rho 1 mu1? Mu3. Here it is, rho 1 mu1, so the product is mu3. But if you do mu1 rho 1, what's mu1 rho 1? Mu1 rho 1, the product is mu2. So as you can see, they are not the same, so therefore S sub 3 is a non-abelian group with 6 elements. Now what else can we notice about this table? Now I want you to notice that the 6 elements in S sub 3 can actually be grouped into 2 groups of friends. Now, for example, we can group the rows, row 1, row 2. Then the ID can be considered a row, right? If we can separate it like this and like that. So there are 2 groups of friends, the rows and the mules, right? What do you notice? The product of rows among themselves are rows again, right? How about the product of row and a mu? You see that the product is a mu. The product of mules with a rows, they are mules. And the product of mules among themselves is a row. Actually, the idea here is that I've named the elements in such a way that the product is easily remembered. If you combine 2 elements of the same type, you get rows as a product. And if you multiply 2 elements of different kinds, you get mules as a product. Okay, so you remember that. So for example, we wanted to know the subgroups of S sub 3. Now, because S sub 3 is not abelian, S sub 3 cannot be a cyclic group. A cyclic group is always abelian, right? So, for a group that is cyclic, we know that the only subgroups are the cyclic subgroups, right? But for a non-cyclic group, there may be other subgroups which are not cyclic, and they are harder to find. Because getting the cyclic groups only takes us to get the powers of the elements, list down the powers. Anyway, every group has cyclic subgroups. So the very first types of subgroups that we're going to list down are the easiest one to get, which are the cyclic subgroups. For example, oh, this is wrong. That's wrong, huh? Hindi kasali S sub 3. This is wrong. S sub 3 is not cyclic. So ID, for example, of course, because ID is the identity, if you take the subgroup generated by the identity, you get the set only the identity. And then, if you take row 1, the powers of row 1 squared, you can check from the table. If you look at the table, row 1 squared is row 2, and then row 1 cubed is already ID. Okay, so you see that row 1 is an element of order 3. You can also check that row 2 also generates the same set. Now, mu1 and mu2, the mu's, by the way, because they are elements which fixes an element and then interchanges the other two, if you notice that, then therefore they are of order 2, because if you switch two elements from a set and then switch them back again, you get the original position. So that's the identity. So the mu's are, well, they are elements of order 2. That's why the cyclic subgroup generated by them only has the ID and itself. Okay, so this one is not included. Ang kulit niya, no? So therefore, these are only the cyclic subgroups. How about the non-cyclic subgroups? Well, S3. By the way, you can see right away that none of the elements generated S3 as a whole, because we are expecting that it's not a cyclic group. So is there any other cyclic subgroups? Well, for at this point, we don't have any other method to generate this. In fact, even in the future, getting all the subgroups is a hard problem in group theory, but we can always try. For example, the identity should always be in the subgroup, so we put the first element to be there. Now, If I put row 1, then all of its powers will be in the subgroup because of the closure property. So I have to put row 2 here. If I close it down now, then this is already mentioned here. So it's not going to be a non-cyclic subgroup, so it's a cyclic subgroup. So we have to add more. But as you can see, if I add mu1, for example, here, then row 1 times mu1 must again be in the set. But what's row 1 times mu1? It's row 1 times mu1. That's mu3, right? Now what is row 1 times, row 2 times mu1? You will see that that's mu2. So as you can see, lalabas lang ulit yung S sub 3. In fact, if you try every other combinations, no, you will find that there is no other subgroups. I just want you to verify this fact. Okay, so this is the complete list of subgroups. And you know that if you have a complete list already, then we can now form the the lattice diagram for subgroups, which is pictured as follows. Again, this is not included here. As you can see, this is a subgroup of order 3. This one. These are the subgroups of order 2. They are on the same level, but they are not included here. Here they are not included there, and then this is the subgroup of order 1. So the lattice diagram is pictured. Now from now on, if we just drop the circle symbol for composition of function and just write alpha times beta if we want to multiply alpha and beta using composition. We only write alpha beta. Okay, so for example, let alpha and beta be as shown. Obviously they are elements of S sub 5. They are permutations on the set 1, 2, 3, 4, 5, right? Alright, so let's calculate beta times alpha squared times beta inverse. So before we can calculate the product, there are two things that we need to know first. First, what's alpha squared? Second, what's beta inverse? Before we can perform the multiplication. So for example, what's alpha squared? How do we do alpha squared? So we just write it here, 1, 2, 3, 4, 5. Then 1, 2, 3, 4, 5. Okay. So we now multiply. So the product will be another element of S sub 5. Right, so we put blanks here. So what's the image of 1? 1, 2, 3. Then 3, 2, 2. So the final image is 2. What will be the image of 2? 2 to 1. Then 1 to 3. You get 3. Then what's the image of 3? 3 to 2. And then here 2 to 1. 1. What's the image of 4? 4 to 5, and then 5 to 4. 4. And then finally 5 to 4, 4 to 5. So here you get a 5. Now how do we get beta inverse? How to reverse a permutation? Well, we just undo the action. For example, you look at beta. Beta, well, of course, beta inverse will be again a permutation from 1 to 5. So you see, beta sends 1 to 4, correct? So how will the inverse undo that? It should send back 4 to 1. So under 4, you have to write 1. That's how you get the inverse. How do you undo sending 2 to 3? You must send 3 back to 2. So you put 2 under 3. Then 3 sent for beta, 3 is sent to 1, right? 3 is sent to 1, therefore the inverse should send 1 to 3. In beta sends 4 to 5, therefore beta inverse should send back 5 to 4. Finally, beta sends 5 to 2, so the inverse will send 2 back to 5. So that's beta inverse. Therefore, we can now perform beta alpha squared beta inverse. So I just write down the 3 permutations involved. 4, 3, 1, 5, 2 times alpha squared 2, 3, 1, 4, 5 beta inverse 3, 5, 2, 1, 4. So you start from the rightmost permutation. Okay, so first prepare 1, 2, 3, 4, 5 here. So we have to know what will be the images of each one of these. So for 1, 1 to 3, 3 to 1, and then 1 to 4. So the final image is 4. For 2, 2 to 5, 5 to 5, 5 to 2. Therefore the final image is 2. For 3, 3 to 2, 2 to 3, 3 to 1. So the final image is 1. 4, 4 to 1, 1 to 2, 2 to 3. This is 3. And I think we don't have any other choice for the last one but to send 5 to 5. In fact, you can verify 5 to 4, 4 to 4, 4 to 5. So that's a 5. So this is the final answer for number 1. Although we don't have a name, right? But it doesn't matter. Take note that S of 5 has 120 elements because that's 5 factorial. Okay? Okay, so for number 2, we are going to find a permutation pi in S of 5 such that alpha times pi is equal to beta. Okay, so how do we do that? So this is like solving a linear equation in a group, right? It's like ax equals b. Well, we have learned that pi can be solved here using the formula alpha inverse times beta, right? So we have to get alpha inverse. So this is alpha inverse. So let me just write alpha inverse times beta all over here. 2, 3, 4, 5, 3, 1, 2, 5, 4. Lagyan natin ng inverse times beta. Beta is 4, 3, 1, 5, 2. Alpha inverse, how do you reverse? Again, 1 is sent to 3, so 3 will be sent to 1. 2 is sent to 1, 1 will be sent back to 2. 3 is sent to 2, so 2 will be sent back to 3. 4 goes to 5, therefore 5 should go back to 4. 5 goes to 4, therefore 4 should go back to 5. So this should be the permutation that will make the equation correct. Now, the reason why permutation is a thing in abstract algebra, why do we bother getting, aside from getting examples for a group, right? For groups, why do we bother studying permutation groups? It is really because of the following theorem. Because Arthur Cayley, well, I don't know if it was really Arthur Cayley who discovered this theorem, but it was named after him. Okay, it says that every group is isomorphic to a group of permutations. Meaning to say, if you have an arbitrary group, no matter how large is it, or no matter how small is that, even if it's finite or infinite, then you can find a set and a set of permutation on that set, so that those permutations will form a group isomorphic to the given group. Meaning to say, if one already knew all the different structures or all the different group of permutations or permutation groups, then it's like saying that we have already discovered all types of groups. In fact, in the future lessons, our lesson will be directed to classifying different types of groups. What are the different types of groups? How do we classify them? So we're moving towards that direction. So the first theorem that we have for the classification is that if you know all the permutation groups, then basically you know every other types of groups, because every group is just isomorphic to a group of permutations. Now, how do we prove the Cayley's theorem? Fortunately, the proof of this is very much easy, but quite there's a lot of detail, so I will try to outline the proof for you. The full proof or the full details of the proof is in your lecture notes. So let's write down the proof. Okay, so here we take an arbitrary group G. Okay, we take an arbitrary group G. So what do we do now? We wish to find, first of all, a set of permutations, and a set of permutations on that set that is isomorphic to G. But what is G? G is any kind of group. So what I do here, so the proof goes like this. You just consider the set S sub G. S sub G contains all the permutations on the group G itself. So we will take all the possible permutations on the group G. So for example, if G has 3 elements, then S of G has 6 elements, right? If G has 5 elements, then S of G has 120 elements, 120 permutations on the group, right? If G is infinite, of course, S of G is also infinite. Normally, if G is large, S of G is larger. That's the idea. So what we do, because S of G is quite a big group, what we do is we will find a subgroup or a subset of this, a quite small subgroup of this, that will be isomorphic to G. How do we do that? So for that, we do the following. For each element of G, let's call it G, I want you to define lambda G from G to G as follows. Lambda G sends every element of the group to G times A, because G is already in G. If you multiply G with A, you get another element of G. So you can think of this as a left multiplication by G, by the element G. You can think of it like that. So lambda G multiplies G to every element of the group. Now you can prove that lambda G is a bijection. Okay, so therefore lambda G is in the set of permutations on the group G. So lambda G is a permutation on G, basically. So what we have learned, or of course, to prove that this is one-to-one and onto, I want you to do that as an exercise, as I am only presenting the outline of the proof. So what we did here is that for every element of the group, we have produced an element of S sub G. So what we do now is we consider the collection H consisting of all the lambda G's. So for example, if G has 5 elements, then there are 5 lambda G's, 1 to each element of the group. That's the idea. Then the next thing that you're going to show is that H now forms a subgroup of G. So how do you do this? Ulit again. This part, you show that lambda G is one-to-one and onto. For this part, you use the subgroup test. Okay. Let me write here a yellow mark. Show lambda G is 1, 1 and onto. So these are exercise. Lagi natin ginagawa to. Ito, use subgroup test. Marami tayong subgroup test. You can use the 1 step or just 3 step. It's 3 steps. It's up to you. Okay. Pangit ng line ko, hindi diretso. So straighten it up. Okay. So now, the final step, so if you now have this subgroup H, the final step now is to show that G is isomorphic to H. So what we did after all is that we were able to find a group, in fact a subgroup of S of G, a group containing permutations that is isomorphic to G. Okay, that's the idea of the Cayley's theorem. I will show you one example later on how to apply the Cayley's theorem in one particular example. Okay? Alright, so how do we show that G is isomorphic to H? So you have to get an isomorphism from G to H. So you have to define the map phi from G to H as follows. So if you have an element G from G, the most natural candidate for the association is the mapping lambda G. Remember, H contains all the lambda G's. Okay? Then you can check that phi is a group isomorphism. And you're done. How do you show that phi is a group isomorphism? There are 3 steps. No? Show that phi is 1 to 1 again, phi is onto, and phi is operation preserving. Do you remember this? Okay, that's it. If you were able to show these details, in fact the details are in your lecture notes if you want to, but I suggest that you do the proof on your own and then try to compare it with how I do the details. Okay, therefore as a conclusion, G is isomorphic to H, which is a subgroup of S sub G. So in English, any kind of group any group G is isomorphic to a subgroup of the group S of G. Now because S of G contains all permutations, right? So every group is isomorphic to a certain group of permutations. That's the Cayley's theorem. Now when you look at the proof, we can derive the following corollary. Okay, every finite group. So this is the Cayley's theorem applied to the case when the group is finite. Every finite group of order n is isomorphic to a subgroup of S of n. So the idea is here, let's say the group has n elements. Okay, then by Cayley's theorem, then G is isomorphic to a certain subgroup H, right, which is a subgroup of S of G. But S of G is just isomorphic to S of n, because if G has n elements, you have the permutations on the set G with n elements, then it is nothing but structurally the same as the set of all permutations from 1 to n. This is what I'm saying. Therefore, we can say that inside S sub n, you can find a subgroup which is just an isomorphic copy of G. Nice, no? Why? For example, if you want to know all the different group structures of order 8, for example, then you only have to look at S sub 8, and then you search for the subgroups of order 8. Then if you look at the subgroups of order 8, then you're done. Those are the only groups of order 8 up to isomorphism. But the group S of 8 is enormous in size because this has 8 factorial elements. Right? How large is 8 factorial? I don't know, maybe 40,000 something. 320, I think. That's how large S of 8 is. So, although the result is very nice now, because it gives us hope of getting all the groups of finite order of a given finite order. Just imagine, no, you're going to get the group of all the set of all groups up to isomorphism of order 100. Then you have to get S sub 100, which has 100 factorial elements. Oh my gosh. And then try to look for the subgroups of it with 100 elements only. And then the different structures that you will see there are the different groups of order 100 up to isomorphism. That's what I mean. Or that's what, although the Cayley's theorem is theoretically good, but practically this is very hard to apply, because normally when you consider S sub n, you are considering a very big group because of the size of n factorial. As n gets larger and larger, you see that n factorial grows astronomically large. As an example, this is what I'm saying. Consider the Klein-4 group EABC. Now, what's the rule for the Klein-4 group? Every element has order 2, so when you take the squares of this, get the identity. And if you take this identity out, if you multiply any 2, you get the third element as the product. AB is C, BC is A, AC is B, so this is also abelian. So what am I saying? For example, what do you mean by lambda E? Lambda E is a permutation on the set, that's why E, A, B, C are present here, so that you get the image by multiplying everything by E on the left, you see? Now this multiplication is now happening in V4. E, E, A, E, B, E, C is just E, A, B, C once again, respectively. Now if you multiply A on the left of each one of these, A, E, A, A, B, A, C, you get this. Lambda B, you multiply B on the left, you get this as products. And lambda C, ganito siya. Ito yung table ng Klein-4 group, ha? So you see, we have produced 4 permutations on the Klein-4 group. You could have replaced EABC by 1, 2, 3, 4. It doesn't matter, right? You just get an isomorphic copy of the group. In fact, that group, if you replace E by 1, A by 2, B by 3, C by 4, then these 4 will now form a subgroup. In fact, this is the Cayley table for this permutation. You multiply them as if they are permutations. You get a group which is a subgroup of S sub 4. For example, you translate this to, let's say, 0, 1, of 0, 1, 2, 3, 4. Yeah? So this corresponds to what? 1, 2, 3, 4. This ID 4. Ito naman 2, 1, 4, 3. Ito naman yung what's this? 3, 4, 1, 2. Ito naman yung what? This is 4, 3, 2, 1. So this permutation forms a subgroup of S sub 4 of order 4. Yung apat na ito, when you try to construct their Cayley tables, it is this. You see that there's a natural isomorphism between the group V4 and the group H containing the permutations from S sub 4. So that's what the Cayley theorem is telling us. In the next lesson, we will still be talking about permutation, but in particular, we will be doing cycles, transpositions, so what are these terms, and how does it help us in understanding the group structure of these permutations. Okay, see you in the next video lesson.